Good evening, everyone. I, Sai Kiriti, Executive Member of IIChE Students Chapter, Sastra. On behalf of the Council, we welcome our Chief Guest, Dr. Sreepriya Vedantam, Principal Scientist in the Process Engineering and Technology Transfer, Department of CSIR, Indian Institute of Chemical Technology, Hyderabad, and our Associate Dean, Dr. V. Ponnusamy, and all our honorable faculty members, alumni, and one and all gathered here. A short note on IIChE Talk of the Month. Every month, we'll be having academicians, industry experts, professionals delivering the talk on their expertise, catering to the professional development of our current and graduated alumni. The idea of having this talk is open to both current and alumni is to create platform of continuous learning such that learning is facilitated by Shastra is not restricted to the actual years on the university campus. Now I request Ms. Vasha to give introduction of the chief guest.
A very warm good evening to one and all present here. I feel privileged to take this opportunity to introduce the chief guest for this occasion. Dr. Sreepriya Vedantam is currently working as Principal Scientist in the Process Engineering and Technology Transfer Department of CSIR-Indian Institute of Chemical Technology, Hyderabad. She received her PhD degree in Chemical Engineering in the year 2007 from Institute of Chemical Technology, Mumbai, in the area of computational and experimental fluid dynamics as applied to process-intensified reactor systems such as annual centrifugal extractors. After this, she had a 2-year postdoctoral stint at Ghent University, Belgium, in the Faculty of Bioscience Engineering. She has worked at CSIR National Chemical Laboratory, Pune, for a couple of years before joining CSIR-IICT. Dr. Sreepriya is a chemical engineering professional with research experience of over a decade in the area of process intensification, including flow processes in miniaturized reactors, multi-phase flows, including phase change, computational and experimental fluid dynamics, design of chemical process equipments, including intensified reactors, process development, and improvement. She carries experience in CFD modeling, integrated modeling techniques, compartmental modeling at various scales as applied to chemical, nuclear, and environmental engineering systems. She has been handling several industrial projects in process development from lab to commercial scale and offering several industrial solutions. She has several research publications to her credit and is a reviewer for few of the peer-reviewed journals. She has also been guest editor for special issues on advances in CFD by Hindawi Publishers and has also conducted invited CFD workshops. Dr. Sreepriya is a senior member of AcSIR and a member of IIChE. She has guided several master thesis students and has PhD students currently working with her. Her current active research includes the area of process intensification, focusing on integrated oscillatory flow reactors, customized miniature reactors, conversion of batch to scalable continuous processes, and multi-phase flows, including phase change. Thank you.
Thank you, Varsha. Ma'am, on behalf of the IIChE Students Chapter, we would like to express our token of gratitude with a memento, and the same will be delivered to you, ma'am.
Thank you, Sreepriya Madam.
Thank you. Thank you,
This
Dr.
is for the
Naren.
memento. The memento will reach your office later on.
Yeah.
Yeah,
Thank you.
Go ahead.
Yeah.
Now, I request our chief guest, Dr. Sreepriya, to deliver her talk on multi-phase flows intensification from a hydrodynamic perspective. Ma'am, please take over.
Yeah. Thank you very much. And thanks for the introduction. And thanks, Dr. Naren. Thanks for the invitation. And it's a pleasure. It's a pleasure to be amidst all the students. And it's a pleasure again to be associating back with you, Naren. Naren is actually comes under the elite faculty of chemical engineering, and it's a pleasure to be associated with you, Naren.
Thank you.
Okay, so I will start sharing the screen. Yep, you can let me know if it is visible or if there is any difficulty with it.
So, are you able to share it?
Yeah.
Okay. So maybe from IIChE, the sharing can be stopped. Probably we can then see that. Yeah, it is now coming.
Yeah, is it visible?
Yeah, it is visible.
Ah, okay. All right. When Dr. Nareen had asked me that this would be a lecture for the undergrad students as well as the alumni, I just wanted to try and cover some of the perspectives from chemical engineering based on my own reflections and my own experience, primarily focusing on how to look at it from a hydrodynamics perspective when we talk about industrial solutions. So that's how I had chosen this topic on multiphase flows and how we look at intensification for industrial solutions from a totally hydrodynamics perspective. I will first start with an introduction about my own organization, the CSIR-Indian Institute of Chemical Technology, which is a part of Council for Scientific and Industrial Research. So I will give a brief introduction about it and the different activities that we take up and what can be the opportunities for either current students or alumni or even experienced researchers for that matter. So CSIR-IICT had originated in 1944, called as CSIR in the Osmania University campus. It was given a place, and that is where it had started its inception, followed by gaining its name as the Regional Research Laboratory of Hyderabad in 1956. And later we had celebrated the Silver Jubilee in 1968-69 years. After which, in 1989, it was renamed as Indian Institute of Chemical Technology, as it had started giving out a lot of technologies or industrial solutions to the industry then. Later in 93-94, we had celebrated our Golden Jubilee, followed by the Diamond Jubilee in 2003 to 4. After which, in 2009, we came to be called as CSIR Indian Institute of Chemical Technology. And finally, we had even celebrated our Platinum Jubilee in 2018-19. And our journey still continues towards excellence, is what I would say. So in all, we hold scientists of nearly 152 with a slightly current increase that is ongoing currently. And we have other technical and non-technical staff of nearly 400. And we do have research scholars numbering up to 400. And we do have several other dissertation, MTech dissertation students or even interns for that matter. Now, as far as the research and development is concerned, we have 10 departments, which include 2 centers. And we do have several services that support the research and development at IICT. And we have a lot of MOUs as be it national programs or international programs. And we basically work under the themes of the healthcare, energy and environmental sustainability, food and nutrition, materials, and specialty chemicals, fluoro and agrochemicals, and capacity building. Then we do have the accredited ACSIR, which also offers PhD programs. So the degree is given by CSIR under the umbrella of ACSIR, which is an accredited institute within CSIR itself. And this is supported by our academic affairs unit of IICT as such. Well, as you know, I come from the Process Engineering and Technology Transfer Department. So just to brief you on what we're trying to do at the Process Engineering and Technology Transfer Department is, previously we were called as the Chemical Engineering Department, wherein we were integrating with the different departments of IICT. And later, because we were dealing with a lot of interdisciplinary research in offering industrial solutions, we changed our name to Process Engineering and Technology Transfer Department. So we work with a vision to promote industrial R&D and also societal welfare, basically focusing in engineering sciences. And our mission is to strive towards engineering innovations and focusing a lot on the translational research in order to meet the industry's demands and also the needs of the society. As far as the core competencies of our department are concerned, we work a lot on the process design, development, optimization, control, process dynamics, safety, design engineering, then product modeling and design, intensifications, and membrane technology. We have offered a lot of services to the industries as part of solutions or in terms of the process development. Then there are several industries that are currently running on IICT-based technologies as well. So here I have just highlighted a few of the success stories in terms of the processes that have been given to the industries. You can see the names which are given here. So all of these processes have been transferred to the industry, and there are commercial plants which are currently running as well at the industrial level. Probably all of you would have heard of the milestone of CSIR's achievement as well as India's achievement, that is setting up of the commercial plant of hydrazine hydrate in Gujarat by GACL, for which the technology has been totally transferred by CSIR-IICT. Okay, now since the students are attending and they are present here, I just wanted to highlight what are the different learning opportunities that we have at CSIR-IICT. So basically, we deal a lot with the undergraduate and postgraduate students' dissertation programs. Then there are a lot of BE Tech students who do their either home papers or 6-month internships, where they have this practice school or the training school programs. So they do come to IICT for research exposure and experience. Then even for the diploma students, that is after the 10+2, who take up the industrial diploma. So we do offer internship programs for them. And of course, as I mentioned before, we do offer PhD research through the accredited ACSIR program. Then there are a lot of postdoctoral research fellows as well who work with us for research experience. Other than that, we do have several project-based positions, and we do offer skill development programs as well for be it undergrad or postgrad, depending on the expertise and the experience. Like we do run a lot of analytical programs, and we do run a lot of skill development programs on CAD-based training or design engineering, or in terms of the scale up. So we do offer several skill development programs. Otherwise, apart from these, there are scientific and technical positions which get opened up normally based on the advertisement, and of course in coherence with our CSIR headquarters. So that is in brief about IICT and the opportunities one can look at when it comes to IICT. Okay, now I will move back on to the topic for today, topic for discussion. Well, I must say here that I have tried to keep this talk a little technical, because all of us are, I guess, our engineers who are attending this talk. At the same time, I have not gone into the extreme scientific detail, because I just wanted to give a flavor of looking at chemical engineering in a more fascinating manner to offer industrial solutions and from some specific perspectives. Okay, and also another disclaimer I would like to make here before I start my talk is there are some of these very generic statements that have been taken from either from the literature or from the groups where I have worked with during my research experience. So it is to be understood, in case I have not specified here, it is understood that I have definitely taken this information from the research groups that I have worked with, and where I have taken from the literature, I have put the citation as well. And also, prior to starting my talk, I would also like to acknowledge the research that I have presented here is includes where I have worked or where I have developed my research experience. Places like ICT Mumbai, then NCL Pune, Ghent University, as well as IICT, where I'm associated currently. Okay. Now, about the multiphase flows, in today's talk, we will discuss about the modular multiphase flow reactors and how they are more enticing as compared to the conventional reactors, and how to look at it from a hydrodynamics perspective as to how this hydrodynamics actually links with the other key aspects which are important when we talk about the performance. Then we will look at very few case studies. We will talk about something like Annular centrifugal extractor, how to look at it from a hydrodynamics perspective. It is an intensified reactor. I will show you more about them. I have tried to choose applications from varied fields where we can directly apply chemical engineering. So I will talk a little about the anaerobic membrane bioreactor from the hydrodynamics perspective again. And then the well-known fluidized bed reactor and some of the industrial solutions as to how they can be viewed at from hydrodynamics perspective, and the oscillatory flow reactors, which we are building currently at IICT. And I will also just highlight on the facility that we have at IICT, both in terms of process intensification as well as the pilot scale facility that we have. And of course, finally, we will close with the futuristic performance views. Okay, so here's what I try to show. What are the miniaturized flow reactors where multiple phases are involved? Now, if you look at typically a conventional reactor that you see here, okay, which has an ability to reduce to the size of 100, which we call as a microreactor, wherein we are referring to the reactors with internal diameters either of several millimeters or even lesser. We can see that compared to the conventional reaction field, in terms of the performance, the performance increases by 10 times when we talk about thermal transfer, and in terms of the mass transfer, the performance increases almost by 100 times. And for this, we are just referring to a channel with a diameter reduced to only 1/10 of the conventional diameter, or for that matter, a cross-sectional area reduced to 1/100th of the actual dimension. So this is how, in general, a microchannel would work. So hence, we call this as more of a multi-modular flow reactor, because we see an enhancement in its performance. So if you look at the time-space relationship for most of the chemical reactions, and if you're talking about space in almost from centimeters to the meters, or even the plant scale, where we are talking about the higher scales, and the time starting from lesser than nanoseconds up to minutes or hours, at the highest scale is where we have the flask chemistry, or as it goes to the plant scale, we call it at the chemistry that happens at almost the reactor level. Now, as we talk about the seconds or lesser, we talk about the flash chemistry. And as it drops down to the nanoseconds and the micrometers of the space, we are talking about the molecular level interactions. But from this, what we see is, as the transfer distance reduces, as you see here, the mass flow and the heat flow here, as the transfer distance reduces, what you see is a rapid increase in the performance. Okay, but how is this concerned with hydrodynamics? Now, when we are talking about hydrodynamics, in all these scales, we will further look at the macro scale as well as the micro scale. We are talking about the behavior of the motion of fluids under the influence of both the internal as well as the external forces. So when we are trying to relate this to understand the pressure forces or the viscous stresses, the different forces that are present, the hydrodynamics is what becomes very important, where we are talking about determining the actual temperature distributions or the concentration distributions in the domain of our interest. That is, we are talking about the reactors. So what becomes important here is, what is the flow regime going to be? And that is the knowledge we gain by understanding determining how the velocity fields are behaving as the flow varies from laminar to the turbulent flow. So if you're looking at conventional reactors, wherein we are talking about larger scale flows, or we call them as the macroscopic flows, wherein we talk about the dominance of convection. So when we say the convection is dominating, there is the turbulent flow pattern that develops. So in this case, if we are trying to convert the physics of the system to the mathematics, or the mathematical modeling in other words, we do not have to actually model the time evolution of these details of the flow field explicitly. When we are talking about the heat transfer or the mass transfer processes, they strongly depend on the turbulent velocity fluctuations itself. So if you are looking at the industrial reactors as such, there have been several reactors which have been designed and also operated based on this significance of turbulence that is actually accounted for in the reactor design for enhancing the mixing in most of the macro scale reactors. So even if you look at the stochastic velocity fluctuations, which are below the scale of the grid resolution also, they are very well accounted for when we talk about the turbulence models. But what comes out to be most important here is how reliable is your mathematical model? How reliably have we converted the physics of the system that is required into the mathematical equations, or how we have gathered the solution of those? So it is that plays a significant role in the design of your macroscopic reactor or the conventional reactor. Well, if we bring the size down to the meso or the microflows, conventionally or typically in microstructures, the flow is mostly laminar. So when we say the flow is mostly laminar, the diffusion paths we are referring to for the heat transfer or the mass transfer, these are also very small. So which means that these become most suited for heat transfer limited reactions or the mass transfer limited reactions. Visually also we can make a statement that our surface to volume ratio is quite high. And what it means to say is that the surface effects tend to dominate over the volumetric effects of the actual channels or the reactors. Considering the reduction in the dimensions of these microreactors, we can say that the actual wall material that contributes more to the process than when you consider the same for a conventional reactor or a macroscopic reactor. Which means that in these cases, the solid heat transfer plays a very significant role. However, if you look at the literature, we do find a lot of information, like you have these catalytic monoliths and several customized microreactors that you find wherein you have selective oxidation reactions are given a lot of importance. Then you have reactions in nanotubes, and you have several of these continuous hydrogenation reactors. So there is a lot of information that is being given, that is available in the literature even now. But what we need to look at is how is it applicable to the actual industry. So when we are looking at these channels, what is it from the chemical engineering perspective that becomes more and more important? Yes, there is physics that is playing a critical role in understanding what is happening in these channels. But what are the different forces and what is the role that they play in terms of the design of the reactor, or what are those dimensionless numbers which can be looked at or which become the design criteria in actually designing your miniaturized reactor or miniaturized channel for that matter. So whenever we are talking about these flow systems, there is always an interplay between the interfacial forces or the gravitational forces, the viscous, inertial forces, all these, which decide how the phase distributions are going to be or how the flow patterns are going to be. So it is this nonlinear or the complex interplay that happens between them that gives the flow patterns that are actually either desirable or not desirable. This kind of interfacial forces, when they are actually combined with the laminar nature, is what results in either the gas-liquid interface or the liquid-liquid interface in these smaller channels. And it is these forces which become very dominant for the microchannel sized reactors. So in all, the bottom line is that the flow behavior depends totally on the relative flow rates of the fluid phases. Hence, the design of these kind of channels or decision on the residence time becomes very important in the design of the miniaturized channels. And like I said, it is the interplay between these interfacial forces that plays a very significant role. So we have the most significant dimensionless numbers which govern the design of these miniaturized channels, like the interfacial force to the gravitational force, which is given by the dimensionless number called as a band number, the bond number. Then the ratio of the fluid viscosities, which is given by the capillary number. This becomes very significant when we talk about these very small channels in which we are talking about either conducting the reaction or, for that matter, even the separation. Then the inertial forces to the surface forces, which we call it as a Weber number. And of course, the universal Reynolds number, be it in micro scale or even in the macro scale, plays a very significant role. Okay, now in all this, where does hydrodynamics actually stand out? Now, why is this wheel of hydrodynamics that important when we are talking about the performance of the reactors? So if we look at the performance as the center target for an industrial performance, so we look at how energy efficient can it be that can decide the good performance of a reactor, which is further dependent on the design. And for the design, the three key important aspects majorly are the thermodynamics, the kinetics, and the hydrodynamics. So if you look at the thermodynamics, the wheel of thermodynamics, wherein we are referring to mostly about the physicochemical properties of the systems that are actually involved, it is this wheel of thermodynamics which actually turns the wheel of the kinetics, wherein we look at more of the reaction control or the rates of the reaction that are involved or that are actually present in the reactor that is due for design. Now, it is these two aspects which turn the wheel of the hydrodynamics, where we talk about the mass transfer and the heat transfer, that finally leads to an efficient design, by which we mean that it is energy efficient, which leads on to performing better. So this is the actual link that exists between the hydrodynamics and the other key aspects which link to the performance of the reactor. So when we are looking at a reactor design in terms of the hydrodynamics, the mixing time scales that we are talking about, they also increase with the characteristic dimensions of the reactor. So what is desirable would be how well we can control or how rapidly we can create a homogeneous reactant mixture as early as possible. And it is this effect of mixing that plays a role on how much the reaction can progress. We are talking about the mass transfer controlled. Hence, I'm saying that, for example, if you're talking about a first order reaction, okay, the residence time becomes more critical. So the turbulent mixing therein may not be that significant. But if you talk about faster reactions, it is the degree of mixing that would determine the yield, because the reaction rate is actually limited by the diffusion rate. So hence we say that it is the effect of mixing actually that is the most deciding factor for the design or for an efficient design. So the same thing, put it slightly in a different manner. Let us classify this as, on one side we are looking at the reaction rate, and on the other side we are looking at the rate of mixing. So when we talk about the reaction rate, we are talking about the chemical regime. When we are talking about the rate of mixing, we are talking about the diffusional regime. When we say diffusional regime, we are saying the mixing becomes rate limiting, which means it's a faster reaction. When we are talking about the chemical regime, we are talking about stating that the mixing is much faster compared to the reaction rate. So your reaction rate becomes limiting basically. But we do have a combined regime wherein there is a mixed chemical or the diffusional one, wherein the interaction between your reaction and the hydrodynamics becomes most significant. And that is what we are talking about when we say linking of hydrodynamics with the other key aspects that are involved in the design of a reactor, which can lead to a higher performance or which is an energy efficient system. So herein, the product distribution would typically depend on the kinetics or the chemical factors and the diffusional factors, wherein we are referring to the mixing efficiency. So under this mixed regime, if we are talking about the time-dependent perturbations of the fluid flow in order to achieve mixing, we talk about the active mixers. And if you're talking about the geometric properties of the channel or the fluidic streams which can maximize the diffusional area, we are talking about the passive mixers. Okay, now I will present to you, this was actually presented in the literature. I think the citation is somehow, it doesn't appear here. So basically, this is presented in one of the papers in the literature, wherein it was stated by linking the performance with the hydrodynamics. Now, as there is a feed that enters the reactor, which is operated at specific pressure, temperature conditions, etc., and which gives out the products. So, if we have to predict the reactor performance, then they talk about the different kinds of modeling, that is mathematical modeling, that is required at various length and time scales. So if you're talking about a length scale varying between almost 10 square meters, and as the length literally comes down to almost nanometer level, we had seen it in the initial space to time graph as well. And if you're talking about time scales of lesser than 10 raised to minus 15 and up to almost more than in minutes or the hours, if you're talking about. Now, when we say at a molecular scale, most of them initially in terms of the length scale are empirical, while in terms of the time scale, we do have either molecular dynamic simulations or we have Monte Carlo simulations, then we have DFTs. Now, as the length scale slightly increases, when we're talking about the eddy or the particle scale, in terms of the length scale, they were more or less empirical, but in terms of the time scale, we do have computational fluid dynamics or the direct numerical simulations. Now, as the length scale further increases and as we start talking about the reactor scale, in terms of the length scale, we do have models for ideal reactors, and in terms of the time scale, we do have computational fluid dynamics or the micro-mixing models. As it further increases and we start talking about the process scale or the actual industrial scale, we are talking about the steady state balances putting in, or in terms of the time scale, we are talking about the actual dynamic models that are available. So primarily, this is how the reactor performance is predicted based on the mathematical modeling and at various length to time scales. Now, in terms of what can be the different kinds of reactors that are actually available, and if we'll try to link it between the mass transfer performance and the heat transfer performance, it had started at initially at the jacketed stirred tank, of course, which is still conventionally used in several of the industries. We name an industry and it is this that is used. However, but considering the intensification that has been brought into chemical engineering, or that has been brought into these scale up and the design of different kinds of reactors, as the heat transfer performance increases or as the mass transfer performance increases, there have been several of the reactors which have come into practice and which have come into practice initially at a laboratory scale and which are also gaining importance at industrial scale. There are several of these reactors where we talk about higher mass transfer performance, like the pulsed column or the static mixer rotating packed bed, wherein with the compromise on the heat transfer performance, we can achieve higher mass transfer performance. On the other hand, if we talk about compromise with the mass transfer performance and a higher heat transfer performance, we talk about plate exchangers or the plate reactors. And then, of course, we do have reactors in this particular map with an optimized mass transfer and the heat transfer performances, where we also talk about the microreactors or the spinning disk reactors. And in fact, in these regimes itself, the annular centrifugal extractor and then oscillatory flow reactors, then all these come into picture, which are advances to the intensification that has been happening either at a research scale or at the industrial scale. So from whatever we have seen as to how the flow variation happens with a decrease in the channel dimension is, if it starting from convection, wherein the turbulent, wherein in terms of the hydrodynamics, the turbulence is most dominant. And as the convection heads towards diffusion, we see that the flow variation goes from turbulent to the laminar regime. And the channel diameter starts to decrease. So if we talk about laminar flow, of course, it is easier to handle, but you have lesser control over time. And there is always a difficulty if you talk about a single channel and you're talking about certain throughput, but how do you take the productivity to a plant scale? So the choice would be either high performance but expensive, and difficulty in terms of numbering up, because when we talk about single small micro channels, we are talking about numbering up, the same synonym for scaling up when we talk about conventional reactors. So we have this choice as to how to choose between bad performance but lower cost with an ease of manufacture, or higher performance but expensive and also difficulty in terms of numbering up. So it is actually this kind of a choice which has led to cutting edge research in the areas of coming up with more and more intensified reactors with different kinds of customization, wherein a much better performance can be obtained, and still there is a lot of scope for work to be done in that particular area to bring from laboratory scale to the actual plant scale. Okay, if you're looking at, let us see, even conventional reactors, can we do something to enhance the performance? Even if we are talking about simple reactors, not necessarily at a simple microchannel level itself. How do we do this? Can we make a simple flow, a single phase flow, quite similar to the multi-phase system, wherein we can enhance the mixing that happens in it so that the performance can be enhanced? So if we talk about longer diffusion times, which typically are with single phase pressure driven flows, these longer diffusion times can actually be reduced by superimposing another flow, which we call it as another instability in terms of both temporal domain as well as the spatial domain. So this is called as, in other words, as hydrodynamic instability. So when this instability sets in, this improves the dispersion and thus it enhances the internal mixing. So there are several intensified flows which are based on this hydrodynamic instability. Like we have the centrifugal instability based Taylor-Cuet flow, where we talk about the annular, the flow in the annular region of two coaxial cylinders. Or, we talk about the variation or the thermal instability, which we call it as a Rayleigh-Benard convection, which happens amidst, either between in a small rectangular channel between two plates. Or the instability which takes place in the vortex form, we call it as a Dean instability. So there are these different kinds of instabilities wherein the flow is made similar to the multi-phase system in order to improve the dispersion in it, in order to enhance the internal mixing that happens. So if we look at it from a hydrodynamics perspective, there are several applications of computational fluid dynamics that can actually be directly applied at an industrial level. Here I have just tried to highlight some of the applications that we generally work with at IICT as well. Well, now how to actually understand hydrodynamics? Well, there are several methods. Primarily, when we have to understand hydrodynamics, the different methodologies are, you have the analytical fluid dynamics, which does have certain limitations, because there is a lot of empiricism and there are a lot of assumptions that are involved. And then another methodology is the computational fluid dynamics, which is quite dynamic, quite robust, but which also needs to be supported by the experimental fluid dynamics. But using these methodologies, what we would come to understand is the actual forces, how they play a role, and how we can arrive at the pressure field, how we can arrive at the energy dissipation or the concentration distribution, and what is the actual flow field like within the reactor. Okay, now having briefed you on the hydrodynamics or its role or how it can be linked with the performance, I'll just discuss few case studies that is compared to the conventional system and what has been the intensified system that we have worked on, and how we have arrived from lab to the commercial scale is what I will try to cover, and I will try to share some of the success stories here. I would first start with an annular centrifugal extractor. So what you see here is basically a coaxial cylinder system in which the inner cylinder rotates. So basically it is the liquid-liquid extraction that what you see here. So finally, the annular zone that you see here, that is the gap between the outer cylinder and the inner cylinder. Okay, so herein there is a mixing that happens, and once it is mixed, the dispersion enters the inner cylinder, which is rotating at a very high speed. Okay, and inside this separator region is where you have your two phases separated out. Now, the principle with which the mixing region works here is the Taylor-Cuet flow. And of course, the separation happens inside your separator by simple centrifugal force. It's basically used for very high mass transfer coefficient applications, also used in several of the industries, especially the nuclear industry, wherein the extraction of ores is quite critical and which requires higher mass transfer coefficients. So there are several applications for this. Now, what I have shown you here is only vertical orientation, but there are several even bio applications wherein horizontal systems are used. When we are talking about this annular zone, we are talking about the sizes of few millimeters, which can give almost a couple of millimeters would actually give you 30 liter per hour throughput. That is what I'm talking about. So in this, basically the design objectives would be how to arrive at the right rotor size, how to arrive at the right height, what should be the annular gap, and what should be the bottom gap when we're talking about the inner cylinder and the outer zone or the outer cylinder, and what should be the overflow vias of the separated phases B, and what can be the optimum power consumption. So these become our design objectives. Now, how do we arrive at these design objectives? Is we first need to understand what the capacities are going to be, what are the physico-chemical properties that are actually involved, what are the equilibria that are there in this, and how do we link this to the actual hydrodynamics of this, which can lead to a right design and thus arrive at the design of the annular centrifugal extractor. Okay, so from a hydrodynamics perspective, the methodology that is adopted here is first flow visualization is done, followed by the computational fluid dynamics simulations, that is both in the annular zone as well as the separator zone. Then there is a comparison that is done between these two so that your models are well validated. You set up simulation strategies. That is where you actually establish a relationship between your hydrodynamics and the design objectives. Followed by the drop size distribution estimation or the mass transfer MTC estimation, MTC prediction. And then arrive at the recommendation of the design parameters and further scale up with which you can actually implement. So basically, this is just to show as to how the flow appears to be in the annular region, though visually it may not be possible. But from your computational fluid dynamics model, you can actually visualize what the flow pattern is going to be like once your model is well validated with supporting experimental data. And this is to show the comparison between the experimental fluid dynamics. What you see here is the PIV graph or the particle image velocimetry based data and the computational fluid dynamics model. Once we have the model well validated, then we establish the relationship between the design objectives and the hydrodynamics based on the flow patterns that we obtain from our simulations. So here we try to see the actual design that is required for the dispersion to be sent into the separator zone. So this information can actually, or this kind of relationship can be obtained from the hydrodynamics models. Now, once this is done, then we look at, as I had shown in the previous slide, we look at the different design parameters and thus design the commercial sized annular centrifugal extractor, which involves several steps, as in the capacity, the requirement, then the drop sizes, mass transfer coefficients. What happens if only mass transfer is controlling, or what happens, like I had shown once in that mixed regime of chemical and the diffusional, where both the mass transfer and the reaction become controlling. And how do you actually determine your residence time? What should be your annulus volume, or what should be the design of your internals in order to arrive at a desired volume? And then go ahead with your optimization and further fabrication. And finally, what we can arrive at is from the laboratory scale to a commercial scale of the annular centrifugal extractor. The work credit here is of Professor J.B. Joshi's group from IICT Mumbai, of which I have been a part of. And a part of this work has been my PhD work. Well, another aspect or another application that we could look at is the membrane fouling that typically happens in the water treatment. So here we are talking about an anaerobic membrane bioreactor. Now, normally you see there is a tubular reactor that is involved. So as there is activated sludge treatment that is done, so the membrane gets clogged. The resistance is built. So there is a difficulty at the plant scale. So how do we arrive at when we are talking about application from or looking at it from the hydrodynamics perspective? So here we try to link the computational fluid dynamics and the population balance model. Then we try to see where exactly is there an accumulation of these particles in the tubular membrane such that the pressure can be varied in order to clear these membranes. So this is the kind of the hydrodynamic application that can be done for anaerobic membrane bioreactor systems. Now, similarly, placement of the internals, when we talk about very large waste stabilization ponds, wherein for such large systems, a direct CFD model may not be more practical to apply to, wherein there is a lot of biokinetics that is involved as well. So we integrate the CFD with the biokinetics model, then we arrive at certain diffusional regimes which act as independent reactors, and we came up with a compartmental model with which we could actually give the designs of internals or the orientation of the internals that improve the performance of these stabilization ponds. So basically, it is this kind of solutions that the hydrodynamics can offer for the existing problems in the industry. Now, similarly, if we are talking about the different aspects of crystallization, the key aspects wherein you have the thermodynamics, kinetic, and in terms of kinetics of crystallization, we are talking about the breakage or the growth of the crystals, or the nucleation and the growth rates is what we are talking about. And when we talk about the hydrodynamics, we talk about the type of crystallizer, or what is the geometry that is critical here. So there is always an integration of all these key aspects which lead to an integrated modeling approach for the overall optimization of the crystallization process. So understanding the key aspects in each process becomes most critical when we are talking about applying this to different scales of application. So that is where the integrated modeling comes into picture. So wherein your hydrodynamics, which is linked with your thermodynamics and the kinetics, still plays an active role. So in this aspect, when we talk about these kind of multi-phase flows, wherein even if you are talking about a simple stirred vessel, the link between your design parameters, like if you're talking about a simple stirred vessel and you want to apply it for crystallization, wherein we are talking about dealing with the solids distribution, what becomes important is to establish the right kind of a link between your design parameters, where we are talking about the aspect ratio of the vessel or the geometry of the internals, and what should be the solids loading like, with the operating parameters like what should be the critical suspension speed, What is the clearance that can be given? And how do you deal with shear sensitive particles? And how much of solids distribution can it actually handle? So it is for these kind of establishing these kind of relationship that your hydrodynamics or the modeling of the hydrodynamics becomes very important. Now, if you are talking about the application of hydrodynamics for industrial solutions, how can you suggest process improvements for industrial processes? So I would just put in a couple of examples here. There was one particular pharmaceutical process scale up wherein the challenge was to scale up a heterogeneous reaction, which actually involves immiscible liquids, from liter scale to almost several of the kiloliter scale, which was actually giving out very low yields and the reaction rates. And the limitation that the industry has is that we can only change the internals, we cannot change the reactor. So then what we try to do is we try to set up this scale-up strategy only based on the hydrodynamics part. What is it that can be done? Why not suggest inclusion of additional impellers? That is, maybe the challenge here is increasing the P by B ratio, because we need to arrive at an increased average strain rate. And try to focus more on the actual circulation time. So what needs to be given here, what the importance that needs to be given here is that one needs to understand the trade-off between the performance and the operating constraints, and accordingly, the scale-up advice needs to be given, which can be arrived at from a hydrodynamics perspective itself or based on the computational fluid dynamics modeling results. Now, similarly, varying batch size in the crystallization reactor. What can be the challenges like? So, and what should be the right kind of design that can actually, design suggestions that can be offered? Maybe if the reactor was originally designed for a specific scale, but it is not performing well for other batch sizes. So what do we do? So how do you optimize on your actual operating conditions, which can make it work better? So similarly for suspension polymerization applications. So in that manner, several of the solutions can actually be offered to the industry. Now, another area of application, like we have the conventional, fluidized bed reactor. Probably you would have all seen this flow regime from, fixed bed up to a transport fluidized bed altogether. So even if we look at a fluidized bed gasifier, what we can arrive at is how the solids volume fraction actually behaves. The most important being the key dominant force in terms of solid particles and the gas phases being the drag force. How does it actually behave? And it is this that is very important in terms of the design of a fluidized bed gasifier. And this is the information that one can actually obtain from a hydrodynamic study. Now, similarly, this can actually be applied even to the chemical looping processes where we are talking about chemical looping combustion or chemical looping reforming processes, wherein we are talking about linking air reactor with the fuel reactor. So the linking of the computational fluid dynamics with the kinetics becomes very, very critical, because it is with this that one can determine what is the interface heat transfer going to be between the gas and the solids. That will actually decide on the actual operating parameters of the integrated air reactor and the fuel reactor in a chemical looping combustion system. Well, those are the macro scale applications that you have seen, some of the intensified reactors. Now, at a smallest scale, but as they say that even small performs way better. So there are several of the applications that can actually be introduced at the industrial scale as well. One example that you see here is that of a continuous emulsion polymerization. So here, what would normally take place in a macro scale at a batch time of close to 5 to 6 hours using static mixer reactor, this could actually be attained within 30 to 45 seconds. With, of course, the product throughput would be smaller here because we are talking about a very miniaturized channel with a static mixer in it. However, this can be numbered up with addressing certain challenges. Basically, because there is a numbering up of reactors that is involved. So you need equal flow distribution. So the challenge will be design of the distributor. And then one needs to address the issues like the channel clogging. So what should be the pressure like? Where exactly should you be applying this pressure? And to understand these, we need to understand what is actually the flow pattern of the reactants inside the reactor. Because for some of these, you do not have right kind of information even on the kinetics. So, and similarly, there are several of the flow processes which IICT has developed, like there is the diazomethane reaction, which is successfully established as a flow process. So there has been a design of integrated safe synthesizing diazocube and also diazopen that has been designed and is already in implementation by Srihari's group at IICT. Then there are several other chemical synthesis routes which have been done in these flow processes. Another example is that of doing this liquid-liquid extraction. Now, how does a packed bed, packed tower work compare itself when worked with a microreactor? So you see that your mass transfer coefficient is almost 30 times higher in microchannels when you compare it with a packed column. And in fact, your macro system here required a very high solvent to feed ratio if one had to achieve the comparable efficiency, which means you need a higher cost of operation. Now, as far as these flow reactors, which we have at IICT are concerned, we do have a lot of assembled flow reactors. Then we do have a lot of chip reactors. Then we have oscillatory flow reactors. We have these oscillatory flow reactors, which are integrated with fluidic oscillators, which generate these auto oscillations and which can be used for carrying out both the reaction as well as the downstream processing. Then we do have commercial flow reactors like the Vapor-Tech, or we do have falling film microreactors, gas phase microreactors at IICT. And this is a layout that we have for integrated continuous flow chemistry, for continuous flow manufacturing at IICT. So we have these different kinds of microreactors which can be integrated with the downstream microscale processing itself as tabletop units and can be integrated and work as a total plant. So basically, this is the layout that I have tried to show here, that these are the different kinds of miniaturized reactors that we can work with at IICT. Now, in addition to this, we do have a lot of pilot plant facilities at IICT. We have glass line reactors of different capacities, up to almost 160 liters. Then we do have different pressure reactors, 50 liter, 100 liter reactors in Hesteloi and SS to cater to different kinds of reactions. And we do have ANFD, which is at 100 liter capacity. We have pressure distillation columns up to 10 bar. And we do have other glass distillation columns of high capacity. We have different sizes of the centrifuge. So we have a huge pilot plant facility. So I would be happy to welcome all of you to see the facilities here at IICT. And however, finally, to summarize, as we have seen in all of this that we have talked about, the fluid properties basically they become increasingly controlled by the reduced reaction or the reactor volumes, which says that mixing can actually be achieved through the diffusion. And it is these miniaturized reactors that exploit this kind of behavior of the fluid based on the diffusion for controlled or the rapid mixing. And for all these, hydrodynamics is the most significant tool, which is very, very critical in design of both conventional and also intensified reactor systems. As I mentioned, on the different methodologies with which hydrodynamics can be understood or can actually be made applicable to the reactor design or the performance of the reactors. The experimental fluid dynamics and the computational fluid dynamics, they are the most powerful tools which are used now in industry for performance improvement, for design of both multi-scale, multi-phase reactors. And there have been several solutions that have been offered for industrial processes with hydrodynamics as tool. Like as we have seen some examples, of course, I have not gone much detail into those. And at the same time, a lot of transformations can also be performed through miniaturization with improved space-time yields or the selectivities, and also even residence times for that matter. However, there is a lot of scope for working in this area, because there is a lot of application in industry that still needs understanding of these parameters, like the scalability of these miniaturized ones, and how can we make it operationally more flexible and more profitable, and so on. Okay, I think with this, I come to the end of my presentation. I think I overshot by 5 minutes.
That's perfect.
Okay. Yeah. Yeah.
Right.
Yeah. I'll be happy to answer if somebody has
yeah.
questions.
So there are questions. So is somebody going to anchor? Who is going to anchor the questions, or can you read? You can also read in the chat.
Okay. I'm just trying to get to the chat window here.
Yeah. So in the Google Meet, the chat window.
Yeah. Okay.
So you want me to read?
It's okay. I have my specs on. I can.
Right. Yeah. Carry on.
Okay. What I see here is similar question as.
No. The first question is actually from me.
Yeah, please.
Right. So at 8:32, which I put the art of simulating multiphase flows. Are you able to catch that?
Yeah, just a minute. I'll just try to move it up.
Yeah.
No. Okay, and yeah, right. Art of simulating multiphase flows depends on two important factors: capturing turbulence, capturing interface momentum exchange factors like drag. What was your simulation philosophy, given that we have CFD groups focused on both of these? Yeah. Okay. Now, number one is, as we talk about these macro scale reactors where convection is most dominant, let us say, no doubt the turbulence plays a very, very important role. But as we talk more about the diffusion in terms of these miniaturized ones, that is, we are talking about microchannels, turbulence does not play a role, but the control of the diffusion becomes very, very critical. So understanding the actual capillary forces becomes very important in those kind of reactors.
Yeah, thank you. You can just go ahead. The next question is from Venkatanathan.
Yeah.
He's actually a final year student.
Right, okay. Yes. How hard is it to pump fluids through a microreactor? Okay, one needs to use high pressure pumps to be more practical, I would say. In terms of pressure drop, won't scaling up add to additional pressure drop and pumping cost? Yeah. Now, the primary challenge, if you're talking about a micro channel, is when we are talking about scaling up, we are talking about actually numbering up. So the global challenge, even as on today, is the design of the flow distributor. So primarily, it is the design of the flow distributor, which is a major challenge in order to get a uniform flow distribution when we are talking about these multiple microchannels. So, however, it is only the initial capital cost, but your operating cost would come down because your solvent quantities would come down, number one. Number two, your efficiency would have gone up close to much more than what you were getting in a batch. However, another thing I want to put forward here is not all processes need to be converted into these miniaturized flows. It is totally depending on the choice of what is the process that actually requires to be converted. Like, because it happens many a times that your batch performs way better. You don't even need to convert it into a continuous process. So it is the choice that needs to be made at that level first. Moving on towards selection for a continuous process. Now, yes, once it is selected, it is the choice of the distributor that is most critical. So there it is going to be only the capital cost, but considering your efficiency, if you consider your actual ROI, you're going to be arriving at it much faster than what you would in a batch process.
Thank you. Just for your adding here, when you said about flow distribution, I just want to add for the benefit of students. Now, if you remember during pandemic, the ventilator flow distribution itself is a very looked after fluid mechanic problem.
Oh, yeah.
Right. It's not that easy in a very small path length to decide the flow for the patients, right? So I just was thinking of that when you said numbering up is actually a problem. It's still an open problem.
Definitely, it's a global challenge even as of now.
Yeah. The next question is from Akash.
Yeah, Akash. Microreactors naturally give better mass transfer characteristics, but beyond some fine chemicals where throughput targets are low and conversion needs to be high, okay, can we economically number up microreactors for high throughput applications? Yeah. Number one, if you're talking about fine chemicals, so we are talking about high value, low volume. Am I right? Who is this? Akash. Yeah. So are we talking about high value and low in volume?
I hope you can hear me.
Yeah, I can. Yeah.
Well, I agree with you that microreactors are really promising for fine chemicals, where we indeed are looking at high value, low throughput applications. But my question is the alternate, the flip side. Is it still possible that we can apply microreactors for applications with really high throughputs, but also really poor mass transfer, and where mass transfer is very critical?
Yeah. So what I would say here is, I was mentioning about arriving at a compromise, okay, between the choosing of this microreactor for a specific application. Now, once you're convinced that, your batch does not give the efficiency that you require, while a continuous process would definitely improve, yeah, then again, when we are talking about numbering them up, like the similar kind of question as before, what comes into picture here is the flow distribution. For the flow distribution, what is important here is what are your multiple phases that are going to be, that would decide, and what is the flow ratio of those that governs your flow distribution. So once again, here the challenge will be the design of the flow distributor that you would be dealing with. So how I would put it here is the sequence is to be judging whether your process requires conversion from a batch to continuous, number one. Number two, whether your flow ratios or your phases permit it to make it easily numbered up in terms of the distribution using a flow distributor. Else, you have another option of going in for a customized, another kind of an intensified reactor, which would allow your chemical or your different fluid phases to flow through easily, giving you higher mass transfer coefficients. So for this as well, there are several different kinds of intensified reactors which are already customized, but there can be still improvements that can be made into these. So does that answer your question?
Yes, it does. Thank you.
Yeah. Okay, so next. Without disclosing any specific information or references, I would like to know what are the possible causes if you meet with failures or not so success stories. In other words, any specific learning from not so good success stories of CFD hydrodynamics? I would say yes, definitely a lot of learning, because there have been some of these wherein, owing to the discrepancies in building a robust model of CFD, that right kind of optimization could not be given. However, based on the learning further down the line, there were improvements that were suggested which had actually worked out well in the industries as well. So typically speaking, I would probably quote an example wherein we were working with very sticky kind of solids. Yeah, it was one kind of a polymer that we were dealing with, and which was it was like almost a dough, but a jelly kind of a dough. So in the initial
So
stage,
it is, sorry to interrupt. So is it like because of lack of understanding of the models, the physics, or sometimes it is lack of not being able to certainly have an experimental data so that you can tune the model?
yeah. Well, to a certain extent, I would rate it to both, Naren.
Okay.
Yeah. So when, as I was referring to this particular case, where we were really dealing with, this jelly kind of a mass, but initially the industry did not want to change the kind of reactor at all. So we just had to work with what was existing in it. So we could not offer a very good solution to them. But then over a few months, we had also done a different kind of a design altogether in terms of a reactor design itself, wherein it had worked out pretty well, and that design as well was based totally on CFD itself.
Oh, that's good.
Yeah. So I think there are a lot of these. It depends on the industry interest, the industry demand as well, and how robust your model, you can make your model to work with.
Fine. Right.
But yeah, I think data for validation plays a very critical role still.
Yes.
But see, computational power-wise, I think now we don't have an issue when it comes to CFD.
Right.
I think, yeah.
No, it has always been the case. Like, I think, at least from our times, if we have been learning that the way the chemical industry accepts or adopts CFD is on a scale much lower than like what mechanical engineers or aerospace engineers would confidently adopt or believe in simulations.
Yeah.
So that's what I just want to add this question.
That's right. But I think now the industry is taking it quite well. They are relying quite a bit on even the CFD-based, CFD data-based suggestions.
Good, nice. We can go to the next question.
Yeah. Okay, somebody says similar question. All right. And then the next one is we're talking about, how is designing of static mixers approached? All right. Come to IICT. I will teach you.
Final year student.
Come to IICT. I will teach you.
Yeah, he's a final year, so he can come.
Oh yeah. We do take these students for home papers. Well, I would say we first start off with building based on literature. What is the data that is actually available, where we have the missing gaps. And then we start with what is the relationship between the actual design that we require and what are the operating parameters. Because, okay, sometimes it happens for a static mixer, yes, we did require CFD simulation, I would say. But otherwise, there are some cases wherein your empirical correlations will really give out very good data. You don't even have to approach the actual core mathematical modeling. But then, yes, for the static mixers, for what we have already done, I think is what you're asking for. We actually started with the literature data to start with. But then there were some discrepancies in the literature data that we had actually come to understand is what I would say. So those we tried to rectify using CFD models. Having done that, with certain alterations to the actually mixer designs, we were able to work for emulsion polymerizations in those. So this kind of a customization we had done to the designs of the static mixers. So we got them refabricated. And that is how we had optimized on the operating parameters of the static mixers that we used for specific application. Yeah, does it answer the question?
Yes, ma'am.
Yeah, thanks. Next. Thank you for inspiring and informational talk. Thank you. I'm Rajshri, doing my final year chemical engineering. I'm intrigued about the skill development program that IICT offers. Can you please shed some light on it? Oh, sorry, I missed something.
Yeah, it's the same. You can go ahead. Can you please shed some light on it?
Yeah, on it and the prerequisites to join the program. All right. Normally, most of the information related to the skill development programs, you can find it on the website. iict.res.in is the website. And these are always floated there. And recently, we had this program on by the design engineering group. They had offered this for the CAD designing and the actual mechanical designing of the equipment. This is one course that I'm talking about. But most commonly, you will find the information on the website itself. The prerequisites for such a course, like the course I was talking about, this was, I think, BTech was required. So prerequisites also are normally posted there. Then there are these other courses on analytical methods. So for that, some of the chemistry background is also required. Then there are some of these courses for some specific kind of analytical equipment, like you have these NMRs and these kind of analytical instruments. So for that as well, the prerequisites are normally posted. So I think my advice would be to go through the website directly and then gather this information, because I might miss out on some of the prerequisites if I state it here. Yeah. Then the next question is to get the idea of how the optimization in the CFD model is done. Typically, how many times the design or operating conditions are modified to arrive at the optimized model? Well, okay. See, once you have your validated CFD model, you first set up your simulation strategies. Once you set up your simulation strategies, then you do not have to do the multiple iterations of modifying your design or operating conditions. So it all depends on how do you develop these simulation strategies, basically. So ultimately, again, it boils down to what is your objective behind developing a CFD model? That is, what is it that you want to look at? Let us say, for example, you're looking for fluidized bed reactor, fluidized bed gasifier, or fluidized bed reactor for that matter. So what is important there is, what is it that actually governs the basic design objective? Then you have to look at your fluidized bed reactor. It's your drag force, ultimately. Okay, so why drag force? Because you need to understand what the solids distribution is going to be like. Right? So that is how you set up your simulation strategies. And that's how you arrive at your optimized model. But it's not mandatory that you modify them multiple times. No, not necessary at all. It is something like experimentally when you're doing it, based on few limited experimental data, you do your DOE, right? Design of experiments. So it is something very similar to that. Yeah. Next. This is Dharnish from final year. I have read that Taylor cured flow reactor is limited by complex design and operation, hasn't made much impact on the industrial scale. Given its potential advantages, are there any recent advancements made to replicate the same to operate Taylor cured reactor in a commercial scale? Yes. Yeah. You can go to the website of Cosner Industries. Okay. There are a lot of direct applications of annular centrifugal extractors worked around in different orientations. Now, previously, owing to its complex design, previously it was only used for liquid extraction applications. But then it was mostly used in nuclear industry to start with. But now you see several of these applications which are being done even for pharma industries, where they are looking at, one is liquid extraction. Then there are some of these, they do this short residence time gas liquid reactions. They use it even for emulsion polymerization. You'll be surprised to know that there are some of these pharma industries which actually use it for crystallization applications. So yes, there have been several modifications to the internals one can have in the annular region. Like some of these applications also deal with the inner part of the reactor, that is the rotor part, not being used as a separator. But it is, of course, it depends on the application that one it is being used for. But yes, there are several applications. Yes, pharma industry does use it, but I would rate it as, let us say, 60%. It is still at pilot scale and not at the commercial scale, 60%. But there are industrial applications as well. Okay, next question. If you interview a fresh undergrad for a project position or internship or say PhD, what you expect or look for in the student? Okay, in many chemical engineering departments, CFD is still not a part of chemical engineering course. Is that still acceptable? Okay. Nareen, I would say I would just look for a student who is willing to do the research.
Yeah. So I'm asking on behalf of the students. So I just want to know how they should prepare themselves for an interview if tomorrow they are going to appear.
Yeah.
They may not know CFD, right? But
It's
they
not
may be
mandatory.
interested after seeing your talk. So I just want to know what you would ask or expect.
Yeah. I would definitely not expect an undergrad to have a thorough knowledge of CFD. I would say for an undergrad, learning CFD could be just a hobby as well. But I don't expect an undergrad to have a thorough knowledge of this. But what is normally expected is whether an undergrad student has the concepts of chemical engineering. Do they understand the concept of the role of heat transfer in chemical industry or in the design of reactors, the role of mass transfer, in chemical industry, or the role of thermodynamics as such. So it is the role of each subject that they learn in chemical engineering in their undergrad course. What is the impact it can have in the actual chemical industry is the knowledge that would be expected from a chemical engineer undergrad for any kind of an internship, or for that matter, even PhD. If somebody is coming for a PhD, the same kind of knowledge would be expected at a certain advanced level. But this is the kind of knowledge that would be expected. However, CFD knowledge is not expected. It is good in a way if the student does not know. It becomes easier to train as long as the student is keen to learn. But yes, the keenness to learn will be highly appreciated in a student. And it's just the concepts that are required and the willingness to learn. That's all.
Thank you. That's nice. I mean, I hope it has reached for whom it is asked. Yeah. The next question.
Yeah, next one. Thank you for showing this beautiful tale about ISSMPAV. Thank you. Suppose I have a lab scale reactor data with me. I have validated the reaction kinetics using physics-based model from the same existing lab data. Okay, now I wish to scale up the same reactor with existing data. What challenges will I have? Yeah. I think for this particular case where you have seen the Taylor vertices, I had given this relationship between the actual design objectives and the hydrodynamics. So challenges-wise, what one has to see is establishing this relationship between the data that you have and your actual design objective. Or, what is it that you would want to do? This is like I was talking about the separation capacities, mass transfer coefficients, like what happens, you're incorporating your reaction into it and also your mass transfer. So to calculate the residence time that is required. So it is only having this relation or building this relationship from the data that you have that is important for your scale up, nothing else. If you have lab data, very well and good, I would say.
It's Bala here. I would like to continue that question. The thing is that
Please.
I don't have validation for the same experiment I'm doing, right? Like I built the whole commercial reactor in the physics-based model, like AcSIR commercial, any kind of software. But I don't have the validation for the same novel reactor I'm going to build in CFD model. How will a journal accept my this kind of approach? They'll definitely ask for validations, as in, right?
Yeah, they do accept, but I think there is a lot of data that is also available in literature in terms of experimental data.
Got it. Okay.
Right. So you could initially use that. Okay. See, that's what, there is a difference between your model validation and your simulation, isn't it?
Correct.
So you first need to have a validated model for which you require basic experimental data. Like, for example, I will just put in a very simple example. A simple stirred vessel, if you're talking about a single phase flow in a stirred vessel, you don't need any validation. Isn't it? It's so well established. Correct. And the CFD modeling approaches that are there for simple single phase flow in a stirred vessel is quite well established. Doesn't even make any sense to validate it, isn't it? Correct. But it is for certain complex designs that yes, this kind of validation is required. So what I would advise is going on this kind of validation with existing experimental data from the literature for some of the parameters, and based on that, set up your simulation strategies and then go ahead with the scaling up of the reactors. It would help there.
Okay. Thank you.
Yeah. From the simulation perspective, how are the subgrid scale details of the flow captured, especially in applications like solid liquid flows? From your point of view, what are the challenges you think might be important to address this question? I would say it is a type of models that one can choose. If you're talking about the turbulence modeling approaches, so how much detail can you go down to is what is important in the choice of your turbulence models. So if you're only talking about solid liquid flows, let us say, so what becomes important is your objective, whether you're interested in actually tracing how your particle is moving, or you're only interested in understanding the overall distribution of the flow. So your challenge would be limited to that. So whether you go in for a discrete phase modeling, or whether you would simply hold on to your Eulerian approaches, is only significant for you. Okay. What is your
the next question is again from Balamurugan. He's also an alumni. I think Sudarshan is also an alumni.
Okay. Yeah. What is your take on physics-informed machine learning for building physics-based models? What are the scopes of digital twins now being employed in the process industries? Yeah, I think in fact, I don't know if you're aware, there is, in parallel, there was a talk on digital twins, I think yesterday or today, I do not remember, but there was this nice talk which is going on. Well, digital twins, no doubt, is gaining importance. But if we talk about machine learning for building physics-based models, see, there are a lot of machine learning techniques which are in vogue currently for product modeling, right? For product design, like catalyst design and those kind of applications. But process design is something wherein there is a lot of scope to build these machine learning techniques. There has been work that is initiated in terms of machine learning for process design, but I think that is something to cash on and to start working with. So there is no doubt there's a lot of scope on it. Okay, and then have you looked into hydrodynamics in a flow equipment such as pump? Frankly speaking, I personally have not done. Okay, but then what is it that you would want to understand about hydrodynamics in pump?
No, I was just interested to know if you have any perspective from your experience on understanding the fluid mechanics in a flow equipment like pump.
Yeah, okay. Maybe I could answer if you have, if you already have done something, and if you had some difficulty, then probably I would be able to answer. But I think I myself have not done for a pump.
Okay.
After the pump I've done, but not inside the pump.
All right. Yeah, no problem. Thanks.
I mean, not sure whether he is interested in, like, if he's pumping slurries, how is that slurry is going to affect probably the internals of the pump.
Okay. Yeah, well, currently you do have slurry pumps also that are available, but the only problem is that there is a specific solids concentration that they can work with. So establishing a steady state flow in these kind of slurry processes, especially when we are talking about these smaller channels, becomes a little critical. There is no doubt about it. But yes, yeah, it is a challenge still, because you can only up to a specific solids concentration.
Yeah, but when you're looking at slurry flows, I suppose it's very viscous and highly concentrated. So so there are like interactions due to collisions, right? So when you're looking at slurry flows, so how will that affect the internal flow structures in a pump, or like flow reversals or shear stress increases, sudden increase due to collision interaction, things like that. Cavitation is another issue in a pump.
That's right.
So so what would be your answer to that, the type of questions?
Yeah, okay. See, no doubt, slurry pumping is a challenge. I do agree with you. Yes, it could lead to cavitation as well. So, if you're targeting to be pump so that a steady state flow with equal solids distribution at every time interval needs to be considered. How I would look at it is, see, now when you're talking about pump, we're talking more about the mechanical design of it, right? So in terms of how the pumping is done and how it is entering your reactor is your requirement, right? Now, yeah, if you're talking about how it is being pumped, now firstly, what is the kind of pump that you're using?
Yeah,
right?
for instance, like a centrifugal pump. Yeah.
Okay. So now in your centrifugal pump, okay, you have a feed, a reservoir. Okay. Now your centrifugal pump is taking it in and then it is sending it into your reactor. Is that what you're talking about?
Yeah, Eventually, it has to go through a pump to some endpoint. It could be reactor or it could be anywhere else. So I'm just curious to know what is going on inside a flow equipment. A pump is just an example. It could be also in a pipe or maybe valves, fittings.
Oh yeah. Oh, that can quite well be modeled. That I don't see it as a problem. No, if you're looking at a flow equipment, I don't see it as a problem. No, because you were referring to a pump, I was talking about it from as a mechanical design perspective. But if you're talking about a slurry flow inside any flow equipment, it can well be modeled with CFD. There's no problem with it.
Yeah. So when you're trying to model CFD for solid liquid flows at high concentrations.
Yeah. So there is a limitation. Yes, there is a limitation in terms of the solids distribution. Yeah, I do agree with it. So how I would handle it is I would only go till the solids concentration for to which my model would work. So I would not go beyond that.
Okay.
Yeah.
But most of the industry cases are dealing with really high concentrated suspensions. Maybe 50% or maybe 55%, which is close to, random packing of any solids. So when you're dealing with high solids concentration like that, so and there are subgrid scale collisions, which is not captured by CFD because there might be resolution limitations in a computational simulation. So in order to capture those very small length distribution of forces, because at such small distances the flow patterns are different, right? Because
correct. Okay, right. See, what I would come to understand here is that as you go to such concentrations, what become more important is how your collisions are behaving as opposed to the actual hydrodynamics because of this.
Do you think, sorry to interrupt, do you think the physicochemical interactions of the solids itself might be one of the factors that might affect the collision?
No doubt about it, because it depends on the frequency of your collisions and the efficiency of your collisions. Right?
Yeah, that's right.
So, yeah. So what I would do is, I would look at what is the frequency of collisions, what is the efficiency of collisions. I would build a kernel to it. Like, what is my frequency and efficiency going to be like? So I would come back with a kernel and integrate that with my hydrodynamics model. Okay. I would have an integrated model of computational fluid dynamics with something like a population balance model, wherein the kernel can be put in as a source or a center. Okay, that is my product of frequency and efficiency could come as a kernel, something similar to what you have as an aggregation, right?
Yeah, agglomerations and
so I would integrate that with the hydrodynamics model and then solve accordingly.
Okay.
So effectively, what I would have is, for lower concentrations of my solids, I would have a validation data which is separately for my hydrodynamics model. And if I have to do it as a standalone BPM model, I would have my model well validated there. But then for the integrated data, I would do it with certain assumptions, but I would build this kernel into my hydrodynamics model.
Yeah, that's interesting. Yeah.
Yeah.
Thanks very much.
Yeah. Next.
Yeah, that's all. I think there are no other questions. You have really, I think, inspired, or there are so many questions. Yeah, I think over to, who is the moderator? You can take it up.
Yes, sir. Thank you, ma'am, for the excellent talk on this auspicious day. Now we are at the end of our event. Now I call upon Ms. Vaishnavi AS to propose the vote of thanks. Please take over.
Good evening to one and all gathered here. I, Vaishnavi AS, consider this occasion as an honor and privilege to propose a vote of thanks. It is said that as we express our gratitude, we must never forget that the highest appreciation is not to utter words, but to live by them. It's a matter of pride for me that I got a chance to thank everyone present here. On behalf of the Students Chapter, I would like to take this golden opportunity to thank everyone who have made this event possible in such great a fashion. I would like to extend our warmest gratitude to our respected guest lecturer, Dr. Sreepriya Vedantam, for taking her precious time out and gracing this occasion with her presence. Ma'am, indeed your words have inspired the students. I would also like to extend my thanks to my peers who have helped in organizing, participating, and thus making this occasion a grand success. Once again, thank you everyone.
Thank you.
Thank you, Vaishnavi. We have come to an end to this event. I thank one and all for making this event as a success. Thank you. Now the recording will be stopped.